Welcome back to linear algebra. Let's just check there's no funky flashcards that are due. Alright, we're good. What did we learn about yesterday then? We learned what an elementary matrix is. What is an elementary matrix? Well, it's essentially you got a identity matrix that has one elementary row operation has been performed on. So basically any matrix that can be converted into an identity matrix with one elementary row operation. And so we learned about inverse operations, which are elementary row operations that undo each other. Okay. Now there's some interesting things here. Every elementary row Now, every elementary matrix is invertible, and its inverse is also an elementary row or an elementary matrix. That makes sense because you have to multiply them together to get I in both ways, and that makes sense because one's going to be the inverse operation of the other. Well, that makes sense. Why? Because that makes sense. But also, if you multiply E times a matrix, so E being an elementary row matrix, it's going to be the same as if you performed the elementary row operation that you did on the I to get from I to E. You'll use that. It'll be the same as basically taking this matrix and just doing that elementary row operation to it. So I think that's almost everything, if not everything from yesterday, the big points. Ow. Okay. Every elementary. Yep. Inverse operations. If you multiply. Yep. Row equivalent. Okay, the only thing we forgot was row equivalent. What is a row equivalent matrix? A row equivalent matrix is a matrix in which you can get basically two matrices are row equivalent if you can get one matrix from the other through only using elementary row operations. So, all right, I'm going to keep reading now. I'm going to jump back in, and then I'll be back to recall what I learned in a little bit. Well, you can call that a record for fastest read-through of a unit so far. We just finished reading right on time section or unit 1.5, which is on elementary matrices and in a way to find matrix, an inverse of a matrix. Pretty cool stuff. So we read the section about equivalence theorem. And what is this? It's actually relating multiple things we've already covered in linear algebra. So essentially, if a matrix is invertible, you know that the matrix also the homogeneous system AX equals 0 has only the trivial solution. You also know that the augmented matrix of that system and the matrix itself reduces down to the reduced row echelon form is the identity matrix. And well, this is all true for an n by n matrix, a square matrix. And finally, you also know that, what was the final thing you know? Oh, that you can express the matrix as a product of elementary matrices. Pretty cool. So you know if any of these things are true, you know all of them are true. If you know any of these things are false, they're all false. So that's super powerful. How can you know that? Well, apparently, I mean not apparently. I'll just explain it briefly. If a matrix is invertible, right? Then take the equation matrix or the equation A times column vector X equals 0. Well, then multiply both sides by the inverse of A. This side becomes I, and this side is still 0. Wait, no. This side becomes X, essentially, and this side is 0. So X equals 0. There you go. You only have the trivial solution being x's only, all the x's are equal to only 0. And then if you know that, well, essentially you can use that to show that the matrix itself, the augmented matrix, can be reduced down to the identity matrix. Just straight, that only, it's all zeros except for the main entries are 1. That's what an identity matrix is. And then I mean that's not a good explanation, but somehow you can explain that, or you can show that from the homogeneous linear system having a trivial solution. Okay. Yeah, basically you can reduce everything else to zeros except for the main diagonal, which will have the x's, or the variables, and then those being equal to 0. So that just being a diagonal 1, and then you have a partition matrix with the zeros. You can ignore this side and just basically unpartition it and just get back to the augmented matrix. And then if you have shown that, then you can say, well, we used a series of elementary row operations to get down from A to I, and so therefore if we can do that, then we can undo it, and so we can show that a product of elementary matrices, which is essentially a series of steps of elementary row operations, can express A. Then we learned the way to we learned a way, golly, dude, what did we do? Oh, the way to find the inverse, a generalized algorithm for finding the inverse. You take the matrix, right? You partition a identity matrix next to it of the same size, and then basically you use elementary row operations on the original matrix, but you do it through the whole row. When you're doing the elementary row operations, then once you get this side, the original matrix, down to the I, then you'll have the inverse of the original matrix. That is, if it is invertible, then you will. If it's not, you'll end up with a row of zeros at some point, and then you know it's not invertible. You know that the matrix can't be reduced down to the identity matrix, which means it's not invertible from the equivalence theorem. So yeah, basically that's because we know that the series of elementary row operations that take A to get I, like we go from A to I, are the same elementary sequence of elementary row operations that will take I to the inverse of A. Okay. So you can know if it's you can tell, and you can tell if a homogeneous linear system has non-trivial solutions based on if the augmented matrix itself can be reduced down to an identity matrix. All right, yeah, there we go. 1.5 in the books. Let's start doing practice problems tomorrow, which is crazy. That was a really quick chapter or unit. Really just about what an elementary matrix is, equivalence theorem, and then finding the inverse. Okay. All right, that's it for you right now. Talk to you tomorrow. See you.